So I'm going to go ahead and introduce Professor Jesse Jenkins is an assistant professor at Princeton University with a joint appointment in both the Department of Mechanical and Aerospace Engineering and the Andlinger Center for Energy and the Environment. He's an energy systems engineer with a focus on how we rapidly evolve the electricity sector, including the transition to zero carbon resources, the proliferation of distributed energy resources, and the role of electricity in economy-wide decarbonization. He applies optimization-based energy systems models to evaluate low-carbon energy technologies, policy options, and robust decisions under deep uncertainty. He landed at Princeton after completing his PhD in engineering systems and master's in technology and policy at MIT. And we're very happy to welcome him here today at Rutgers. And I'll take this opportunity too to remind you guys of talks coming up. Burson Unel is March 13th in IFNH at 10:45, our typical Rutgers Energy Institute slot. And then also Dave Spence will be down at Blaustein March 26th at 2 p.m. So, but thank you.
Great. Thanks. It's good to be here at Rutgers. I just made the move down to New Jersey in September or August, so I'm getting settled in. So it's great to be able to come up and visit my neighbors here at Rutgers. And I'm excited to share a little bit of a sneak peek of a big study that we've been working on at Princeton for a while. I sort of joined midstream, looking at how we're going to get the overall U.S. economy to net zero greenhouse gas emissions by 2050. And I'll zoom in particular to focus on the role of the electricity sector in that transition, and that's where most of my work, my research focuses on the role of the electricity sector. So I'll start with why net zero. Why are we talking about this goal in our study and in this talk? And it's really interesting. When I started working on academic models and studies looking at zero emissions in the electricity sector or net zero goals for the overall economy, it was really an academic topic. And that wasn't that long ago. I published my first paper on this question of deep decarbonization in the electricity sector in about 2016, and we started working on it a couple years before that. And at that point, we were talking about 80% reductions in economy-wide emissions by 2050. That was the Obama administration's stated goal. Number of states, including New Jersey, Massachusetts, had state commitments to similar levels of decarbonization. So going all the way to zero emissions was kind of a hypothetical. Let's see what happens if you push everything all the way to the end. Well, in the intervening time, just in the last few years, we've seen a spate of different states and jurisdictions, other countries, committing to net zero greenhouse gas emissions for their whole economy, so not just the electricity sector, but economy-wide, and all greenhouse gases, in either statute. Hawaii was the first to legislate a net zero emissions law in 2017, I believe, 2018. And then in the last year, both Nevada and New York State have enacted legislation targeting net zero emissions economy-wide by 2050. 3 states, California, Montana, and Massachusetts, have enacted similar goals via executive orders from their governors. And I imagine this map will populate more and more over the next few months. If you've been following along the industry news, this is the hot trend as well amongst the sort of at least sustainability conscious or brand conscious companies that are trying to make their companies seem consistent with a climate focused society. So a bunch of utilities, now up to 6 major utilities, have committed to net zero greenhouse gas goals for their whole utilities companies. 3 airlines, Delta, Qantas, and at least JetBlue for their US portion of their fleet. And then most recently, BP made a lot of news in the last couple of weeks for committing their company to net zero emissions by 2050, including scope 3 emissions, which are all the emissions associated with the products that they sell. So not just their operations, but all of their fossil fuels they sell. And Repsol actually beat them to the punch and did that. The Spanish oil and gas company did that a few months earlier. And then there's several heavy minerals and materials companies, Vale, which is a Brazilian iron ore mining company, Heidelberg Cement, which is a big European producer of cement, and ThyssenKrupp, which is a big steel producer in Europe. They've all made similar goals. So these are all heavy emitting sectors of the economy where major companies are committing to try to dramatically reduce their emissions down to zero, at least in net, with offsets, which is something that some of these companies, I won't point out any in particular, are relying heavily on. All right, so it's not just companies or states. The federal government's getting in on the act, at least the Democrats are. So here's New Jersey's own rep here and chair of the House Energy and Commerce Committee, Frank Pallone. The House Democrats on the Energy and Commerce Committee outlined legislation initially in November and then again in December that have a number of co-sponsors. I think we had over 150 co-sponsors for this initial bill, and all of the leadership in the House Energy and Commerce Committee side have supported another bill that would take, there's a number of legislative measures that would commit the U.S. To net zero emissions by 2050. There's a similar, much briefer Senate bill that just dropped as well. So there's sort of action on both sides of the House and Senate towards commitments to net zero. And of course, if you've been following along the presidential debate, every single one of the Democratic presidential candidates has some version of a net zero emissions pledge in their campaign platform. I think almost all of them by 2050, with the exception of Andrew Yang, who tried to one-up everybody by committing to 2049. Bloomberg didn't make the stage in this debate, so, but he is also committed to net zero by 2050. So where is all this coming from just in the last year, right? None of this was on the radar about a year ago. And I would argue that it's largely the result of the popular discussions around the UN, IPCC's Intergovernmental Panel on Climate Change report on global warming at 1.5 degrees Celsius. This is a special report, came out in 2018, and outlined both the impacts and the differential impacts of 1.5 degrees worth of warming versus 2 degrees, and what will be necessary to cut emissions globally to reach that goal. And it was pretty unequivocal that, at least from the global perspective, getting carbon dioxide emissions to zero and greenhouse gas emissions to net zero was the only way that we could stabilize emissions. So this is a number of different integrated assessment model scenarios that all achieve a long-term global warming equilibrium of 1.5 degrees Celsius with differing degrees of overshoot. So the gray is we could overshoot a little bit more and go more negative in the future, make up for it. And the lighter colors, the blue is limited or no overshoot. And what they found is that sort of the bulk of the scenarios all converge to zero emissions globally for CO2 sometime between 2045 and 2060. And they had about a 50% reduction in emissions by 2030 or 2035. The report also mentioned what it would take to do 2 degrees Celsius, which is a target that the international community committed to at the Paris Climate Accord, with an aspirational goal of 1.5 degrees. And that would mean a central window of sometime between 2060 and 2080 globally to get carbon dioxide emissions to zero. And then all of these scenarios involve taking emissions to negative after that of CO2, which means we have to pull more CO2 out of the atmosphere either through biomass or through chemical, energy-intensive chemical means, and then sequester that CO2 underground. In order to reduce atmospheric concentrations of CO2. And that's due to two things. One is that we might overshoot in the near term and temporarily lead to higher concentrations of CO2 than would be consistent with a 1.5 or 2 degrees goal. And the second reason is that I'm not showing the non-CO2 greenhouse gases here, chiefly black carbon, methane, and nitrous oxides, which in most of the scenarios don't go all the way to zero, particularly methane and nitrous oxides, where agricultural activities, both fertilizer and natural sort of anaerobic digestion in animals and in wetlands and rice paddies, aren't expected to fall all the way to zero. We might be able to cut them in about half. And that means that we have to offset those non-CO2 greenhouse gases with further reductions of CO2, where we have more control over the lever. So that's the challenge. There was a lot of public, sort of translation of this report into, statements like we only have 10 years left to confront climate change, or it's all over, or we have to cut emissions to zero by 2030 or 2040. Sort of taking these global targets and using them, for the U.S. specifically. And what I wanted to point out just before I move on, this is not my area of expertise on climate impacts. There are probably folks in the room where it is. But the report makes a really good job of explaining that there isn't a really, like 1.5 obviously is just a round number, right? 2 degrees is a round number. And these numbers come out of political processes and are meant to convey sort of relative levels of risk. But if you have 1.155 degrees of warming, right, that's not the end of the world. Each of these issues have this chart shows a number of different impacts on Earth systems and human systems from differing degrees of warming, and they represent the degree of confidence in different transition zones in these highly nonlinear complex systems. And there are very few of them are hard thresholds. Some of them, like mangroves, maybe are pretty close to a hard threshold. But they're all over the place, and the general takeaway is that every 1/10 of a degree matters. And if we can keep global warming to 2.1 versus 2, it's better than if it's 2.3 or 2.5 or 3. And so any of those goals ultimately require stabilizing atmospheric greenhouse gas emissions from human activities to net zero. Otherwise, we're continuing to accumulate climate warming gases in the atmosphere. And so regardless of whether we're trying to get there on a 1.5 degree time frame or a 2 degree time frame or a 2.2 degree time frame, the goal remains get to net zero as rapidly as possible. And I think it's that as fast as possible that's the interesting question, right? Because that's where the rubber meets the road. That's where the politics matters, that's where the policy drivers matter, that's where the technology matters, and that's where we're falling behind, right? We can say, net zero by 2030 all we want, but it's whether we can bend this curve that so far has been flat or increasing to rapidly and sustained declines that will determine how quickly we get to zero. Okay. So I'll also argue, and this is not a scientific statement, this is my personal normative statement, and let me be clear about that America should lead and not follow. And that means that if the global average is to get to net zero by, say, 2050, the US really should be leading that charge, not right in the middle of the pack. And that's because we both have arguably a moral responsibility due to our cumulative contribution to greenhouse gas emissions, where the United States is the largest contributor to cumulative emissions. We're now the number 2 annual emitter behind China, but if you look at the total warming we've incurred so far, the US is the most responsible of any country in driving that warming. And second, we have the technological and financial means to lead, right? We have the wealth, we have the technological capability, and we should deploy that in a way that makes it easier for other countries to follow. So leadership isn't just about doing the right thing and standing on an international stage and saying, look, we're cutting our emissions, why don't you cut your emissions? It's also about harnessing technological capabilities in countries like the United States and our higher wealth and willingness to pay for maybe a higher cost of energy in the near term to drive down the cost of solutions to climate change over time. And when we do that, it makes it easier for other countries to follow, particularly other countries that don't have the wealth and means to pay much more for electricity or energy than they would otherwise. So leadership is not just about demonstrating our commitment, it's also about using our wealth and our willingness to lead to drive down the cost of solutions and make it easier for other countries to follow. All right? So our report, the Net Zero Study, is focused on this challenge of decarbonizing the United States, and we're really trying to think about how this would happen, what it would cost, what the infrastructure that we'd have to build out to get there would look like, and where it would be built across the country, what are some of the implications for employment or air pollution, trends in different sectors. And this is a study that's led by Eric Larson and Chris Gregg at the Andlinger Center and myself. And we have a big team of scholars as well, Steve Bacala and Rob Socolow, who many of you probably know, have been providing leadership roles in this as well as a number of researchers and postdocs, consultants, and others. The report is funded by the Climate Mitigation Initiative and the Andlinger Center, which are in turn supported by BP and ExxonMobil. And we have a broad consultative committee, including both BP and Exxon, but also the NRDC, Environmental Defense Fund, the Nature Conservancy, Clean Air Task Force, and others that are providing input on the study direction. And our plan is to have this report out by September as a potential blueprint, a technical blueprint for policy discussions that we hope will follow in 2021, say, when there may be political opportunities for legislation in the United States. I want to argue that while this report focuses on net zero by 2050, it's very clear that that means that the time to act is actually now. That we can't wait to plan this transition till later. And that really, for many investment decisions, 2050 is the day after tomorrow. It's not a long way away. 30 years might sound like a long time. But if you look at just stock replacements, which is the turnover of certain durable assets in the energy system, things like light bulbs, complex fluorescent light bulbs might last for 3 to 5 years. So we might get a number of shots at upgrading our lighting systems into more efficient lighting systems. Certain appliances might last for 10 or 15 years. Air conditioning and furnace systems, so HVAC systems, you might only get 1 or 2 turnovers between now and 2050. Vehicles, similarly, the average car or truck is on the road for about 15 years. So we have basically 2 stock turnovers between now and 2050. Commercial boilers last even longer. And for things like power plants and pipelines, decisions that we make right now and investments that are being made tomorrow will still be operating in 2050. So we're already starting to constrain our space to maneuver between now and a net zero 2050 economy. And if you replace a vehicle, say with an internal combustion engine vehicle with an electric car at the time of purchase, the time you already have to roll over that vehicle, it's relatively inexpensive to purchase an electric vehicle instead of a normal car, an internal combustion engine, right? But if you have to scrap a perfectly new car a couple years after buying it and buy a whole new vehicle, that's a huge additional cost in the spend that we have to incur. So thinking about the pace of capital stock turnover and when certain investments need to be made, some of them sooner than others, is what drives a lot of the modeling behind this study and the sort of analysis of when we have to make this transition in certain sectors and how quickly. Because if you can make the transition in time with the normal capital stock turnover of certain infrastructure investments, it's a relatively affordable proposition. If you have to, if you miss the chance to when those stock investments are made, and you have to go back and shut down a perfectly new gas plant or a new pipeline, for example, or encourage sort of cash for clunkers, encourage people to trade in their cars early, then things get a lot more expensive. Okay, so that's why we have to plan very clearly now, and why we need policy and market conditions in place that are driving investments in the right direction. We already spend 4% of GDP a year on energy. In that order of magnitude, right? So if we're spending that wisely and just move it from dirty to clean, we can make a lot of progress without spending any more. Turns out we do have to spend a little bit more, but not a huge amount. Okay, and if we don't plan ahead, it's very likely that we'll encounter dead ends. Dead ends in terms of infrastructure, where we built things that really are inconsistent with a net zero economy, and where there's a political incentive for the from the interests that own those assets to fight change because of that. And also dead ends from a technological perspective, because it takes time to develop new technologies and improve them. If we don't start today, we won't have the suite of clean technologies we need in, say, 2030 or 2040 to complete the job of decarbonizing the economy. So it took us 20 or 30 years to make solar and wind cheap technologies. I'll show you the stats on that in a minute. That didn't come out of nowhere. That came from proactive public policy support for a number of decades. And so if we're not supporting the kinds of policy development, the technology development that we need to complete the portfolio of resources now, then they won't be available when we need them. And that's why studies that plan out what mix of technologies we might need in the future are really important to today's decisions, not 2050's decisions. Okay. So let's start by sizing up the challenge. This is our reference scenario, which is based on demands for energy services from the US Energy Information Administration's annual energy outlook. And what you can see is this is the sort of total primary energy demand for different types in our economy. And you can break this into two categories, basically. The first is a set of electricity, hydrogen, biomass, and steam, which are services that can be directly decarbonized through substitution, right? We have clean electricity sources we can use for this chunk. We can make hydrogen from clean renewable energy or nuclear power, or we can make it from biomass. And steam, similarly, we can make steam with either hydrogen or biomass or resistive heating from electricity. So this 23 quads of energy, quad is a quadrillion British thermal units. Just note that they're big. We consume about 70 quads in total of energy services. And a primary energy demand is more like 100 quads. So this is sort of 1% of our primary energy supply, maybe 1.5% of our energy service consumption. So a quad is big. We consume 23 quads, which is about a third of our total, from things that we can pretty directly satisfy with zero carbon electricity if we wanted to. Then comes the harder part, which is that the remaining 2/3 of our energy consumption is pipeline gas, liquefied petroleum gas, diesel and gasoline, jet fuel, et cetera. So compact fossil fuels that are difficult to immediately replace with clean sources. We don't have a clean natural gas alternative or a clean oil alternative, right? So what are our chances here? Well, we can try to meet this 46 quads with several different options. We can use energy productivity improvements, either efficiency or mode shifting or just conservation, to try to knock down this total. We can electrify some of the end uses, which then moves them from this category to this category, where we can substitute clean electricity. We can try drop-in zero-carbon fuels, so we can make biofuels, or we can make Fischer-Tropsch fuels, so that we can take hydrogen and CO2 and upgrade them through chemical processes into synthetic hydrocarbons, either methane or diesel type or kerosene type fuels. Or we can continue to use some fossil fuels and then offset those emissions with negative emissions from either biomass with carbon capture and sequestration or direct air capture, where we're pulling CO2 out of the air. That's basically our set of options. And what that leads us to is a sense of basically 6 pillars of decarbonization that we need to pursue in some combination to get to net zero emissions across the economy. So the first is energy productivity or efficiency. I term this in terms of productivity because we think a lot about energy efficiency policy measures, but most of the gains in energy intensity improvement or productivity improvement aren't related to what we think of as traditional energy efficiency programs. They're steady improvements in the productivity of individual industrial processes, just economizing over their costs of inputs. And they're due to shifts in the overall makeup of our economy from more energy-intensive sectors like manufacturing and agriculture towards less energy-intensive sectors like services. Right? So a bank or cloud computing or things like that produce a lot more GDP or wealth with less energy inputs. So the fact that our overall economy is shifting more towards services is driving a lot of energy productivity improvements that are sort of unrelated to efficiency. And then a subcomponent of those gains are from things like efficiency policies, like more efficient windows or lighting or vehicles. Okay? So 2 factors there. The second big one is electrification. So we can electrify more of our end uses, and that allows us to substitute clean electricity, which is the third one. So clean electricity supplies. Electricity is about 1/3 of our emissions today, so we can knock that out right away. And the more we electrify other end activities, the more it can, the bigger a role clean electricity can play in the total solution. Then we can develop net zero carbon fuels to substitute for the remainder. Use carbon capture and sequestration to both capture direct emissions from industrial activities like cement or steel production, or to capture process emissions from biomass conversion, which could then be a negative emission source, to do direct air capture, or to enable power plants to continue to use natural gas or other processes to continue to use natural gas, maybe coal, but natural gas is more compelling in North America, without net emissions of CO2. And then finally, one of the big ones is to enhance the land sinks under our control. So the wetlands, agriculture, forestry lands all can absorb CO2. They can also become sources if we don't manage them well. And the net land sink in the country, if we enhance it, is enough in our calculations to offset not quite all, but nearly all of the non-CO2 greenhouse gas emissions from methane and N2O, nitrous oxides, if we can cut those by about 50%. So this plays a pretty big role, not in the energy sector, but in enabling, all the math is fungible, but the way we think about it is the land sink itself, if we enhance it and we reduce the land-related emissions from methane and nitrous oxides by about half, can more or less cancel each other out. We still need to get to about negative 170 million metric tons of CO2 to offset the remainder, but we can get pretty close to offsetting all of that. So the land sink plays a pretty big role, and we do some sensitivities where what if we don't enhance that quite so much, or we can't cut our methane or N2O emissions quite as much, and it makes the energy sector part a lot harder. So this is all very important in the agriculture and land use sector to make sure that we're netting out, we're first reducing direct emissions in that sector, and then using other activities in that sector to net out as much of the remainder as possible, ideally all of it. Any questions on the land sink part? I probably won't come back to that for the rest of the talk. Okay, so I'll focus for the rest of the talk on electricity, which I argue is the linchpin in this strategy, right? It's not all of it. I want to say it's the only thing we have to do. But as you'll see, it plays a huge role, both in sort of these 2 areas here, and then in producing net zero carbon fuels in some cases. Carbon capture fits into the electricity sector, and you'll see the electrification even delivers some energy productivity improvements too. So here's our reference scenario. And in this study, we constructed 2 electrification scenarios. One that I would basically say is full electrification, right? We threw as much as we could of electric vehicles, heat pumps in buildings for heating and cooling, electric boilers and industrial processes wherever possible, et cetera. So we sort of pushed it to the limit. And then we have a scenario we call electrification constrained or delayed, where we push the full saturation of these markets back 20 years. I'll show you what that looks like for vehicles in a second. But what it means in terms of the total overall energy consumption is first that the combination of efficiency improvements, which we bake into all of our scenarios, aggressive improvements in end-use efficiency, helps drive down our total final energy consumption by 20 to 30%. And that's a combination of both efficiency improvements and productivity improvements from final energy consumption to services improvements from electrification itself. So one thing is having a more efficient building envelope, right? So that it consumes less energy to heat it. The other is that a heat pump is much more efficient at converting energy input in the form of electricity into comfort than a gas boiler. Same with internal combustion engines versus electric motors. So an electric drivetrain for a vehicle is probably 3 times as efficient at taking energy from the battery and getting it to the wheels of the car than an internal combustion engine is at taking energy from the tank of the car and turning it to the wheels of the car. So those combinations of end-use sort of improvements in efficiency and electrification themselves drive total final energy consumption down in these scenarios between 20 and 30%. So we save 13 to 20 quads right away just from that. Second, you'll notice that electricity expands dramatically, particularly in the high electrification case. And that's important because in combination with improvements in final energy efficiency, that drives down the remaining demand for hydrocarbons, pipeline gas, diesel and gasoline, jet fuel, et cetera, by 40% in the delayed electrification case and 60% in the high electrification case. And that turns out to be really key because if we can't knock down that demand, we simply don't have enough biomass to supply all the rest of it, right? Which is the easiest way to make zero carbon substitutes for gaseous fuels. And so the more we can knock that down, the more we can use sustainable sources of biomass to meet most of the rest of this, and then produce some synthetic fuels to do the remainder. Here's a sense of what the electrification pace entails, though, to be on the high electrification rate. This is the new sales, so not the stock. The stock on the road lags behind this by quite a bit. But this is the new sales of vehicles of different types in the 2 scenarios. And yellow is electric vehicles. And so this is light-duty cars, light-duty trucks. So these are all the personal vehicles. Medium-duty trucks and heavy-duty long-haul freight trucks. This is, so I was saying yellow is EVs. This color here is hydrogen fuel cell vehicles, which play a pretty big role in the trucking sector as well. And then we have our remaining gasoline, diesel, and hybrid vehicles here. So anything that isn't yellow or this light greenish blue are conventional fossil type fuels. Now we could substitute out the gasoline for some biofuel or something, but we'd have to find a way to substitute for that. So what this shows is that we reach 50% of new vehicle sales from electric or fuel cell vehicles by 2028 in the auto industry, or 2028 for cars, 2033 for everything else. Right? So that's not that far away. Auto manufacturers plan their stock their new vehicles 3 to 5 years in advance. They have to invest in new manufacturing facilities and tooling to produce these cars. They've got to do a lot of marketing to sell them. And that's really just starting for EVs that reached about 2% of vehicle sales in the United States last year and actually went down from the previous year. So we're not quite on track for this yet, or at least we're down here, but we would need to ramp it up real fast over the next decade, such that by 2033 we are at half of vehicle sales. The other scenario, that we don't reach half of new vehicle sales from electric or fuel cell until 2038 for cars and 2043 for everything else in the delayed scenario. And then we reach 100% of new sales by about 2045 in all sectors in the high electrification case, and 80 to 90% by 2050 in the other scenario. The stock, as I mentioned, falls behind this, right? Because vehicles last on the road for about 15 years, so it takes a while for them to turn over. So if we get to 100% of new vehicle sales in 2045, we're not even at 100% of on-road vehicles by 2050, even in this scenario. We hit there probably 2055 or 2060. So this is one of those areas where policy could play a really big role, is sending a pretty unequivocal signal that we're moving towards electric vehicles. And some countries have stated that they're going to ban internal combustion engine sales, like France and the UK, by a certain date. The US has not done that yet. I would expect certain states would probably start doing that soon, like California, because there's really it's the best way to make the math work on this. Interestingly, in this case where we delay the electrification, I would have expected that the total demand for electricity in that scenario is actually lower. But it turns out that the only substitution for electrification is actually more electricity. So the reason for that is that if we don't electrify those end uses, we still have to decarbonize them. So now we have to make more synthetic pipeline gas or diesel or gasoline or jet fuel. And in all these scenarios, we've already used up all of the available biomass that we give it. So we have two different scenarios, low biomass, high biomass. Low is not really low. It's 12 quads of energy from biomass, which is, a fifth of our total, or a sixth of our total consumption. So it's a huge amount of biomass. And the high biomass case is from the billion-ton study from the US DOE, which is basically all the possible biomass we could get in the US economy. And that involves converting a lot of land that's in marginal production now into agricultural production. It has all kinds of knock-on effects, both domestically and globally for conservation, food prices, et cetera. So this is not a scenario to be taken lightly. In the low biomass scenario, what we tried to do is basically say, we already use 20% of our prime corn production for biofuels. Right? So we're using prime corn agricultural land to produce energy. Why don't we take that same amount of land and convert it to higher yield crops like miscanthus or switchgrass, but not increase the total production of prime farmland. And we'll use some of the conservation lands that are set aside to keep prices high in the agricultural sector to produce biofuels as well. And then we'll use waste, which is a very small amount, waste biomass. So this scenario, the main gains in biomass production come from converting corn lands to produce other bioenergy crops that are higher yield. That means getting rid of the whole ethanol industry, which is not an easy thing to do. But at least the math could add up that we could do that without any net increase in US land devoted to agricultural production for energy. Okay. So and even in this scenario, we see when you can, in both cases, no matter what level of biomass you have, we're using basically all of it, all the cheap stuff anyway, before we get to the point where we're constrained by the electrification pace. So if we don't electrify the end uses, we can't just use more biomass. And so the alternative is to do electrofuels, or power to gas or power to fuels, where we take electricity from hydrogen, electricity to produce hydrogen, and then we either take CO2 from biomass or direct air capture, and we make Fischer-Tropsch fuels for liquids, or we do methanation processes to make synthetic natural gas. It's all very energy intensive, takes a lot of electricity, a lot more so than if we'd actually just electrified the end uses themselves. So it turns out in those scenarios, the total demand for electricity to run all these non-final energy demands, so the gray is the actual direct consumption of electricity, and then these are the intermediate fuels, electric boilers, electrolysis, and direct air capture, where we have to actually use more electricity to offset the emissions in those scenarios. So it's interesting that we may be delayed on consumer uptake of these technologies, but it actually doesn't reduce, it actually increases the importance of clean electricity to getting the job done. So I found that surprising and pretty important, that there's no way around a substantial increase in the amount of electricity we supply, and it all has to be from clean sources. So that's what this looks like. These are our four scenarios that I just showed you here. So our high electrification and electrification delayed are the two colors, and then high biomass and low biomass in the dotted line. So this is sort of the range of electricity demand growth between now and 2050 across all those scenarios with the lines. And you can see that in all those cases, we're talking about a doubling or more of total electricity consumption by 2050. That's even as, remember, total primary energy demand or final energy services demand falls by about 20%. So we're not using more energy over in the overall economy, but we are relying doubly on electricity than we do today. So this is why our electricity is really the linchpin. And at the same time, this is our mix of current electricity sources. So our annual energy production from different sources of electricity. It's about 60% fossil, natural gas on the bottom in red, and coal in black. The remaining 40%, luckily, is already decarbonized. We get 20% from nuclear, and the other 20% from a combination of renewable sources. Hydro and wind, about the same share, at about 6 or 7%, and then the remainder from biomass, solar, and geothermal. So if we keep all the clean stuff, and at least half of the existing nuclear by 2050, that's what we assume here, that half the fleet has to retire because it's old. The other half we can relicense out to 80 years and keep it going all the way through 2050. then the fossil we have to phase down to hit our emissions reduction goals in these scenarios. So coal entirely disappears in all our scenarios by 2030. The most cost-effective way we can cut emissions rapidly is to replace coal with a mix of natural gas and renewables. Okay, so that's the first thing that happens. The coal goes away. And the second is that our natural gas total burn starts to decline as well until 2050. So this is the current stuff that we have. And then if we just take the gap between these new demand scenarios and what we have, that's the new clean energy that we have to bring online every year or in each of these years. All right? And that looks like this. So we just took the difference between this line and these bars in each year. All right? So these are the growth trajectories for clean or carbon-free electricity that we need in the United States. And for context, this is all carbon-free generation we have today, so 40% of our electricity. And what this means is that sometime between 2027 and 2028, depending on the path, we need to double all of our carbon-free electricity in the next 7 or 8 years. This is all US electricity generation. So it took us 150 years to build our current generation fleet. We need to build all of that from new clean sources, the equivalent of all of that, sometime between now and 2038 or 2037 and 2040. So the next 17 to 20 years, just call it 20, right? And then, depending on the pace of growth, we have to do it all again by 2050 because it's going to double, right? So this is not business as usual. This is not an easy task. And if you want to do all this by 2030, as certain presidential candidates want to do, go ahead and shift that whole timeline up, right? So laudable goal, but the pace of change is just staggering that you need in the electricity sector, right? Already, just to get to net zero by 2050, let alone 100% clean electricity by 2030. So here's some context. If we take this rate of growth, this is all electricity generation, we turn it into a sense of sort of the raw capacity that we would have to build. And we talk about average gigawatts. So a gigawatt is a unit of capacity. You don't run every power plant all the time, right? A nuclear plant runs close to all the time, but a coal plant run half the time. A wind or solar farm maybe 35% of the time. So if we just multiply the total capacity by the utilization rate, or what's known as capacity factor, you get an average gigawatt. So we'll call that an average gigawatt of capacity. And this would be the equivalent, and so a gigawatt is, I should say, is about enough to supply about 1 million average US households all their electricity for a year. We consume about 1 kilowatt on average. So 1 million households, or one large 1,100 megawatt nuclear power plant like the AP1000, one large nuclear reactor's worth of output a year. Okay, so this is the average pace of additions across the next 30 years is somewhere between 28 and 37 average gigawatts. So 28 to 37 average new nuclear power plants worth of carbon-free electricity every year. Doesn't have to be a nuclear plant. I'm just using that as a big unit of energy. And unfortunately, that's a lot faster than the rate we've been going. So this, for context, is the average rate of new non-hydro renewables, so wind, solar, biomass, et cetera, between 2010 and 2018, which is the last year that I have good data for. And it was 3.4 average gigawatts. So we need to be going about 10 times faster than the rate that we were bringing online renewables over the last decade. And the peak single year was 2016 for combined wind and solar additions, which is the average about 5.3 average gigawatts in that 1 year. So we still need to be going sort of 6 to 7 times faster than that. And if we go back in time further and we scale it based on our much larger population today, we brought online a sustained rate of 7.4 average gigawatts of new nuclear adjusted for population growth. So this is a per capita weighted term, between 1981 and 1990. So even that, we need to be going 4 or 5 times faster than the peak sustained decade of nuclear expansion in the 1980s and 90s, right? So that's pretty daunting. If we look at other examples, we start to see a few things that get close to the ballpark we're talking about. So Germany has been a leader in renewable energy deployment. They're going about twice as fast as we are in the US in per capita terms. So if you weight to the German, size of the German population versus ours, they're bringing online a peak of 12 and an average of 6 average gigawatts a year in the last decade. So still not quite there, but at least we're getting closer. The US natural gas building boom in the 2000s was the biggest sustained addition of any new generating capacity we've had in the United States. In a single year, we brought online something like 60 gigawatts of new natural gas. And the average over the 2000 to 2010 period was 23 average gigawatts. So now we're getting pretty close to at least the range that we're talking about here, 27 to 35 gigawatts. And then the two fastest sustained decade-long rates of expansion of carbon-free generation we can find globally, if adjusted for GDP or for per capita terms, are nuclear build-outs in France and Sweden in the 1980s, where France brought online a sustained rate of 26 average gigawatts worth of carbon-free power, and Sweden about 30 over that decade. So now we're in the ballpark. If we could sort of do something similar as France or Sweden in their nuclear expansions, or something close to what we did with the natural gas boom in the US, but sustain that for 30 years instead of 10 years, then we're talking. Now we're in the ballpark, okay? And this is a little bit scary, but I also look at this and I say it sends a pretty clear message, which is that if you get the market conditions right, as was the case in the US market in 2000 when we started to deregulate natural gas and wholesale electricity markets, caused a flood of investment into the sector. Or if you get the policy conditions right, where you had state-led utilities building out large amounts of new nuclear using standardized designs, then you can see sustained investment in new energy infrastructure on this time frame and this pace. But only under those conditions. That's all the examples we can see. And even when we throw a lot of subsidies at renewables, we haven't yet seen that kind of sustained growth. The only other one I could put on this chart, if we did it in per GDP terms, would be China's build out of coal. And if you do it per capita, it doesn't rate because China's so much bigger. But if you do it in per GDP terms, that would be right in this area as well. So if you get the right sort of state or market conditions in place, then maybe we can see this kind of sustained growth, but only under those conditions. And if we kind of dither for another decade without the right policy and market signals, we'll be way behind the pace that we would need to get to net zero. So the next big takeaway from our report is that renewables take center stage in this electricity market, right? So today, wind and solar are less than 10% of our electricity. And in all of our modeled scenarios by 2050, they're centerpieces of our electricity system in the way that coal and natural gas are today. The reason for that is that we've seen sustained declines in the cost of wind and solar and batteries, which are supportive of their growth, over the last decade. And we expect that to continue to some degree over the coming decades. So just in the last 10 years, we've seen the cost of solar, the average cost of electricity from solar, fall by almost 90%. And the average cost of wind by 70%. Those are staggering cost declines. And I think they're also the other reason, in addition to sort of the focus on net zero in the IPCC report, why we're now talking about these ambitious, bold political goals. Because when I used to work on renewable energy policy from 2006 to 2008 in Oregon, and federal policy from 2008 to 2012, we were still talking about costs for solar that were in the $300 a megawatt hour range. And wind, if you could get wind for $100, that was golden. Now they're $35 a megawatt hour. They're cheaper than new natural gas plants. They're approaching the levelized cost of just the ongoing fixed O&M and fuel cost of existing coal plants. But that's a total game changer in terms of the economics. It's why you've seen a bunch of utilities committing to sustained and deep reductions in their emissions, because it now makes so much better economic sense than it did a decade ago. So what we see in our scenarios, if we just look at the sort of the bookmarking around the four, the high electrification, low biomass, and electrification constrained high biomass, this is solar, and this is wind, and this is offshore wind. So this is our total electricity supply. And you see they just come to dominate the total electricity mix by 2050. Or not all of it. We still get about 20% of our electricity from other sources. But they supply sort of 60 to 80% of our overall electricity, which is on par with what we've traditionally relied on natural gas and coal for. So that's a huge shift. In order to get there, you won't be surprised given the previous slides, we need rapid sustained growth rates in wind and solar. So these are the 5-year average capacity addition rates. This is not in average terms now. These aren't average gigawatts. They're gigawatts per year averaged over 5 years. For wind and solar, ramping up from current levels, which are about this, is what we expect in 2020. We expect about 18.5 gigawatts of wind to come online this year and 15.5 gigawatts of solar. So that's where we are kind of in the 2020 to 2025 range in each of these scenarios. But then it's got to keep sustained ramping up rapidly from there. And by the final decade, we've got growth rates from solar and wind that are faster than the world record single year expansion rate in any country, which is China. In 2017 for solar, we brought about 54 gigawatts online, and wind, in 2015, we're about 30 gigawatts online. So we're talking about, in these cases, very high rates over time. But if we can keep the sort of compounding growth of the sector going, then you could potentially do this. This is a 100% renewable scenario that we ran. Again, not by 2030, but by 2050. And you can just see the dramatic increase in the total pace of renewables additions that you would need to do that. Not just because we can't use any natural gas or into the CCS or nuclear in the electricity sector, but this is 100% renewable economy-wide. So now the only way to since we're not using any fossil fuels with offsets anywhere in the economy, the only way we can do that is to produce more synthetic natural gas and Fischer-Tropsch fuels from electricity. So this scenario relies on a lot more electricity than any of the other scenarios. It's about a 10-fold increase in total generation instead of a 100 to 160% increase. And so it's just a huge amount of total electricity needed to do that. We also ran a renewables constrained scenario where we say, what if we can't build any faster than the peak year that we've seen so far? And in that scenario, and that's sort of the only one, we see a big ramp up in nuclear and natural gas as CCS to sort of to fill in the gap. And if when I look at these scenarios, I sort of look at the scale up rates for both renewables, which I'm showing here, and the non-renewable clean electricity sources in this scenario, which require really staggering rates of nuclear build out to make up for the slow renewables growth. I think somewhere in between those two scenarios is probably a pretty feasible pace of growth for the sectors.
So more Fischer-Tropsch from electricity is not going to be the other way around, like more electricity from Fischer-Tropsch?
No, so we're doing power to fuels. So we're making hydrogen from electricity and then upgrading it. And we're taking CO2 either from direct air capture or biomass sources.
So when you consider that, sorry, I missed that.
But the FT does produce some electricity back into the system too. We count for that.
If you consider biomass one of your scenarios, I don't remember if it was low biomass or high biomass, but you consider direct capture, right?
Yeah, yeah.
So basically, during the process of producing, for example, like Fischer-Tropsch, like capturing as well.
Exactly. So all of the biomass plants, almost all of them, are fitted with CCS to do BECCS or biomass to CCS. And that allows us then to use a little bit of fossil fuels left in the economy. It's still down dramatically from today's levels, but we still use probably on the order of 10 quads of fossil fuels for things like jet fuel and some pipeline gas that are hard to decarbonize. And that's what's not in this scenario. And that's why this scenario is so much more renewables focused, because we're not allowing any residual fossil use in those scenarios. And we've already maxed out the biomass. And so we have to use a lot more electricity to produce hydrogen in these scenarios. But yeah, biomass and CCS, we both see a lot of BECCS hydrogen production. So we gasify the biomass to make hydrogen, and then BECCS Fischer-Tropsch fuel processes as well that take carbon from biomass and produce liquid fuels. And both of those processes capture the CO2 so that they're net negative processes, which can offset residual fuel use elsewhere.
What is the indirect? Considering also the indirect, right?
The upstream, the life cycle emissions? Yeah, so we don't consider that directly. The high biomass scenario probably has some land use implications globally that we're not accounting for. We try to constrain the biomass in the low case so that it doesn't compete with other food or land use needs. So we're just taking the biomass from the corn ethanol. So that was the idea there. So we're not doing a full life cycle assessment of what happens globally. Yeah, so this scenario is a little more suspect on those grounds. Okay, so even though renewables take center stage, they don't quite fill out the whole job, right? So it's not 100% renewables unless we force it to do that. This is now capacity, not energy shares. But you can see that this is our reference scenario, and today's levels in here. We have about 1,000 gigawatts, or a terawatt, of total installed capacity in the United States from fossil or thermal sources, dispatchable, non-renewable sources. And that actually stays pretty close to true across all of our scenarios going forward. This is storage on the top here in purple, but we still have about 800 gigawatts of firm or dispatchable generation in these scenarios, even when we have high renewable shares. So why is that? Well, in my closing minutes here, I'd like to pose a riddle, see if we can answer it. This is a statement from David Olson, who's on the California ISO Board of Governors. This is the California Electricity System Operator. And they recently, an article was quoted as saying, interestingly, it can be more expensive to add cheap solar to our system than to add expensive geothermal. sort of like a Buddhist riddle or something, right? How is it more expensive to add a cheap thing than it is to add an expensive thing? So let's see if we can answer that question. We'll use some data from the ISO New England, since that's where I used to live, so I pulled their data. And we'll just do a simple kind of electricity system simulation. This is not what I use in my research. It's a spreadsheet model, but it helps illustrate some of the dynamics at play here. We've got 4 different options for our electricity. Natural gas, which costs about 5.5 cents a kilowatt hour. Wind, which costs about 4. And solar, which costs about 3. And then we have a clean, firm technology. This could either be expensive geothermal in the west or new nuclear in the east that costs 7 cents a kilowatt hour. So a lot more, double the cost of the solar. All right? In this initial scenario, we'll assume we're just not going to build any of that expensive stuff. Take it off the table. We don't support it with policy, or we preclude it, or whatever, because it just looks too expensive. So forget it. And we'll focus just on these technologies. This is the annual chronological electricity demand throughout the year. So you can see we get some spikes in the winter months when it's cold, and then the high peaks in the summer when it's a hot summer day and everybody's running their air conditioning. And then we're going to start requiring a growing share of clean energy in the mix. Start with 20% clean energy. And that's what all of the yellow lines are there. It's actually all solar to start with. The model picked solar because it was the cheaper option. Remember, it's 3 cents a kilowatt hour instead of 4 for renewables. So it starts by picking solar. And this squiggly line is kind of hard to look at, so we'll change it into what's called a load duration curve, which just orders the load not chronologically, but from the highest hour of the year to the lowest hour of the year. So now you can see some things easily. Like this is the highest amount of demand. It's 34 gigawatts. And this is the lowest amount of demand throughout the year, which is about 16 gigawatts. This is known as the base load. And then this strip here is the contribution in each hour from the renewables. Okay? And we'll combine wind and solar for ease. So right now it's all solar, but when we start adding some wind later, we'll just add it all into this common strip here. So we can see that we're getting 20% of the total area under the curve, which is our total electricity consumption from clean sources now, and 80% from the brown here, which is our natural gas. Up here are some dials that give us a sense of the value of these resources. So we'll start with the energy value for wind and solar. The energy value is that for every megawatt hour of the fuel, of clean wind or solar I generate, what am I displacing? And if it displaces natural gas, we'll treat that as 100% energy value. So 100% means that every megawatt hour I generate from the next wind or solar facility that I add to the system is going to go to displace a megawatt hour of natural gas and save the 5.5 cents a kilowatt hour that we said it cost. Okay. Then this is the capacity value, which says for every 100 megawatts of wind or solar capacity do I add, how many megawatts of natural gas can I shut down permanently? Because I don't need it to meet our peak demand anymore. And here you can already see that wind and solar have very low capacity values. And that's because the net peak, which is the time we need the most firm capacity, is September 8th at 5 p.m. And we need 33 gigawatts of firm capacity at that time from natural gas. And it's 5 p.m., so the sun is setting and the solar output is fairly low at 4% of its maximum. And it's not particularly windy. It's a high pressure front over the region, and so there's not much wind. So the capacity value of wind is 9%. In other words, it takes 100 megawatts of wind to displace 9 megawatts of natural gas capacity. And it's 4 gigawatts substitution for every 100 gigawatts of solar. And then we'll have a dial here, which will go up later, of overgeneration, the total amount of wind and solar we produce that exceeds our demand in any given hour. We either have to store that, which comes at some cost, or we just have to curtail the wind and solar output, and then that energy is wasted. Okay? So now let's start raising the clean energy share and see what happens. So at 40% clean energy share, the first really interesting thing happens, which is that even though solar was cheaper than wind, we stop adding solar and we add about 5% of this mix from wind instead. Right? So cheaper solar, more expensive wind, and it's actually cheaper for the system to start adding the more expensive renewable already. We're starting to get an answer to our question. And the reason is that the energy value for solar and wind fall at different paces. Their output is all correlated, right? It's due to the weather. And the solar output tends to be more correlated, right? It's all spiky. It comes out in the middle of the day every day, and particularly more in the summer months than the winter months. Whereas the wind is a little bit more random. It maybe has some seasonal trends, but it has this kind of a longer form random walk type signal to it. So it's less concentrated in the same hours. And what's going on here is that in these hours here, we're getting all of our electricity from solar and wind. So ignoring the fact that you have to keep some gas plants online for reliability purposes, let's assume you can turn them all the way down to 0. And in these hours, we can meet 100% of our electricity demand from wind and solar. In fact, more than 100%. This is overgeneration here. It's equal to 3% of annual consumption if we could somehow use it and move it over here. But what happens in these hours is that because we've already displaced natural gas, additional wind and solar in that hour now has a fuel-saving value of 0. Because the other resource it's displacing is just some other wind or solar facility with no fuel cost. So the solar energy value has fallen to 77%, which means that 23% of the output for the next solar farm that I add is concentrated in these periods here where we already have enough wind and solar. And only 77% of it is concentrated in these hours here. So the wind is more spread out, so only 9% of its output is concentrated here, and its energy value is 91%. So that means for the next megawatt I add, 91% of its generation occurs in these hours and displaces natural gas, versus only 77% for solar. Does that make sense? Because they have different production profiles. The net peak is the same. Overgeneration, as I said, is now 3%. So when we go to 60%, something interesting happens, which is that the net peak jumps from September to August 19th at 6 p.m. So we were contributing a little bit of capacity value during that net period, right? 4% for solar, 9% for wind. And that meant that we were actually pushing down that net peak a little bit. But we pushed it down enough that now August 19th becomes the highest period of net demand when we need the most natural gas. We still need 31 gigawatts, down only 3 gigawatts from 34 at the start. And because it's even later in the day, 6 p.m. and even less windy, the solar and wind capacity values fall even further to only 2%. And we actually get a shift in the total shares. We actually want more wind now than we wanted solar. We start to see some nonlinearities in the effects. And then finally, we go to 80%. We get a huge increase in the amount of overgeneration because most of the solar and wind we have to add capacity to try to displace this stuff. But most of its production is concentrated over here. So the more we're getting here, we're getting 2 or 3 times as much output in these hours. So the overgeneration problem starts to run away too. We're now generating enough here to meet 28% of our annual energy demand. And the solar energy values fallen to 1/5 of what it started at and 1/4 for wind. So if we relax the constraint at the beginning that we are not going to allow any of that expensive, clean, firm stuff, the geothermal or the nuclear, we actually see that we want some of it. Even though it was twice as expensive as the solar, and almost twice as expensive as the wind, we want it in our mix. And that's because its energy value is high, because it can concentrate its production, it's dispatchable, in the hours when we need to get rid of gas. So this amount of its production here is concentrated in the periods of 0 energy value. But the rest is all 1-for-1 displacing natural gas. So it maybe has an 80% energy value. And it has a 1-for-1 capacity substitution because it's always there when we need it on the firm, the clean, the net peak day. And so it has 100% capacity value versus only 2% for these technologies. So what we get is a mix of different technologies, all of which cost different amounts. And we actually end up with the smallest share of the cheapest technology, the solar. So this is where I like to argue that comparing technologies on cost is like comparing the cost of a banana to the cost of a burger when you're trying to decide what to eat. So you hear a lot that, like, I said it earlier in the presentation, right? Solar and wind are now cheaper than new natural gas plants. That's good information to know. It's better than if they were more expensive than new natural gas plants. But the fact that the banana is cheaper than the burger doesn't really, it's useful information, but doesn't tell you everything you need to know when you're trying to decide what you want to eat, right? You wouldn't only eat bananas. You wouldn't only eat burgers. Your doctor's certainly going to yell at you for that. And in fact, what you need is a balanced diet with different nutrients and a mix of different foods. And in fact, the more you eat of a particular type of nutrient, the less valuable it gets, right? The first banana is good for potassium. But you eat too many bananas, and the potassium is probably not good for you. The same is true for the energy mix, right? It's the complex diet, the combination of all these technologies, and the different value, or nutrients in this metaphor, that they provide to your diet or your energy system. So I'll just close by saying solar and wind are going to be stars in this mix, right? They can be our center. This is our point guard on the Princeton women's team who's kicking butt this year. But you can field a basketball team with 5 point guards or 5 power forwards, right? And you're probably going to score some points. But you're going to lose every time to a team that has all the right players and all the right stars and all the right positions on the field. And wind and solar and even batteries can be stars in this mix, but they're not going to round out the whole team. To complete the team, We need a set of firm low-carbon technologies that can substitute for natural gas and coal plants, which play this role today. We can get a lot more from wind and solar and run-of-river hydro and these other variable renewables, which I call fuel-saving technologies, because as we saw in the previous example, they have very low capacity value, but a lot of fuel-saving potential. Then we have a set of technologies that deliver fast bursts of flexibility or balancing, which are valuable complements to solar and wind. And this is where battery storage is playing a bigger role, but also demand response, which is curtailing demand when prices are high, or demand rescheduling, right? If I need to charge my electric vehicle at a certain time between now and when I go to work, I don't really care exactly when I do that. I could schedule it around the availability of wind and solar or the price of electricity, right? So that provides a lot of flexibility and value, but on short time frames. You can't run your battery forever. You can defer to charging your car for a few hours, but not for a few weeks. And you're not going to sustain demand curtailment for any long period of time because it has a high opportunity cost. So what that leaves is a critical wedge of firm technologies. I define firm as technologies that can generate energy any time of the year for any length of time for as long as needed. And that makes them critical complements to weather-dependent variable renewable resources and energy-constrained or short-term balancing resources like demand response and batteries. And if we have all three, we see that that's consistently the low-cost portfolio. We don't need every technology on this list to be in either of these categories, but we do need one or more in each of these categories to fill out a low-carbon team and complete the clean electricity transition at the lowest cost. And since different technologies are available in different regions, right? The West might tap geothermal, but we're not going to do that around here. Carbon capture you can only do in certain areas. We're probably going to need a mix of these technologies to decarbonize the whole country because certain ones will work in certain regions. And I'll just argue that, we've got a lot of policy support for solar and wind, a lot of policy support increasingly for batteries, and relatively little for these technologies, which remain relatively immature and or costly compared to wind and solar. That's fine. We don't need them for the next decade. But as I said at the beginning, technology takes a long time to mature and improve. And the reason that solar and wind are cheap now is because we took the last 2 decades to make that happen. We supported them with policy. We supported them with R&D. We supported them in their growth and maturation and improvement, and that drove down the cost steadily. We did the same thing for shale gas. We did the same thing for nuclear 30 years ago. This is how we make clean energy cheap. And we have to do the same thing for these firm low-carbon technologies as well. I'll leave it there. Thanks.
Take a few questions.
Yeah. Sure. Awesome.
What are your thoughts on the Energy Master Plan and specifically Rocky Mountain Institute's integrated energy plan? If you've had a chance to look at it.
Yeah, I haven't had as much time to sit with it as I'd like, but it's pretty similar to ours for perhaps a non-surprising reason that we both used evolved energy research to do our modeling. So EER was the modeler for Rocky Mountain Institute that did all the scenario analysis for the Energy Master Plan. And we hired them to do the modeling for our study as well. So you run these models, they produce pretty consistent results, which is that you have this big pile of emissions and you got to get rid of them. And the same core strategies are at play in the Energy Master Plan. New Jersey looks a little different than the country as a whole, and so some of that is going to be different. We have a bigger role for offshore wind, for example, than the nation as a whole. Our emissions, a larger share of our emissions come from transportation than the economy as a whole. So those are big areas where I think there's more focus in the master plan, and they get a lot more into policy than we do in our report. Our report is meant to be a sort of technical foundation for policy discussion, not a set of policy recommendations. We're actually starting there's a new National Academy study that's starting up that Steve Pacala and I from Princeton are both on the committee focused on the policy recommendations for deep decarbonization. So we'll kind of pick up where our report left off at the national stage. But I think it's really cool to see more and more states actually doing this kind of detailed planning. Massachusetts is in the middle of completing a 2050 roadmap study as well. I'm on the academic steering committee for that, and they're making quite a lot of progress. And the exercise of really just doing this full accounting, what we did for this study, but on a state level, trying to understand where all the emissions come from and the fairly limited set of levers we have at our disposal to pull on, really clarifies things pretty quickly about what we need to be doing. And so, New Jersey's focused on ramping up electric vehicle sales, for example. That's a big piece of this. They're focused on 100% clean electricity, focused on keeping our existing nuclear reactors running, since that's sort of the clean foundation to build upon. And if we have to both replace natural gas while replacing the nuclear. It's a lot harder to do that. So there's a lot of stuff in that plan that I think makes a lot of sense. In some ways, the hardest sectors, the ones we're just starting to tackle now, are buildings and heating, which in our scenarios see pretty rapid uptake of heat pumps. And we really don't have much in the way of kind of coherent policy in place anywhere really on that, which means we're going to fall pretty quickly behind the pace in our high electrification scenario unless things change. But the report starts to tee that up as well and focuses on that also. So I think these planning exercises are really useful, not necessarily for the plan themselves, but for the process of planning. And we're going to have to update that plan continuously over the next few decades. But as long as we keep looking out ahead, updating on our progress, the planning exercise itself is very clarifying, I think. Back.
Wouldn't your stock replacement that showed on the very bottom one was a pipeline?
Yeah.
Wouldn't that say that we shouldn't be building more pipelines?
Yeah, I mean, we are looking pretty closely at that in our study. I don't have a definitive answer yet, and it probably differs by region. But for the overall economy, all of our scenarios involve a reduction in pipeline gas use, which would imply a reduction in the need for pipelines. And a big reduction in end-use gas demand. So some of it is still bulk gas for making hydrogen from steam methane reforming with carbon capture is one option in some of our scenarios, or carbon capture natural gas plants. Those just use the main pipelines. They don't use the distribution pipelines. So there's going to be a really interesting dynamic that we have to figure out between the interplay between a growing electricity sector and a shrinking end-use natural gas distribution sector in many parts of the country. It doesn't necessarily go all the way to zero, because having some hybrid gas and electricity in some of these sectors still makes some sense. But it's going to be more and more costly to maintain that distribution network with less and less users. So yeah, there's two big questions. One is main pipelines. I think there's still a role for main pipelines in most of these scenarios, but maybe less than we have today, which means building new ones is questionable. And then in many cases, a pretty substantial reduction in the role for distribution pipelines, which are the bulk of our costs right now. And interestingly, a lot of these utilities are joint, including PSEG, are joint electric and gas, right? PSEG is public service electric and gas. So they're on both sides of the equation, and that could be good because, from a political perspective, because if their business cannibalizes their own business, maybe they don't care. But it also means there might not be as much competition going on. Although my friends in California, at least Southern California, like to point out that SoCalGas, which is a standalone gas utility there, is really fighting for its existential life in California, given the policy environment there. And they're throwing everything they can at stopping a lot of these policies. So, we'll see. I don't know which works out best in the end. Yep.
If I look at the future state that you're outlining here and the current state that we're in now, I'm interested in your opinion on what changes need to take place first. And I categorize the changes as policy, laws, regulations, finance, investment and business models, technology, and sociology.
Yep.
What needs to take the initiatives first? Is it policy, laws, and regulations?
I mean, that's the thing that we as a society have the biggest lever over, right? The biggest control over is policy, and policy can shift investment and can shift behavior to some degree. I don't have a detailed set of policy recommendations for you yet. That's what we'll be working on in the National Academy study. What we're going to try to do very clearly with our report is to outline what are the infrastructure transition changes that need to happen first and when, particularly over the next decade. And so what it looks like for us, we sort of take a step back from this. We need to be rapidly increasing sales of electric vehicles in all segments. We need to be building out a much more robust transmission system to tap into better renewable resources and also to prepare for the roughly doubling of total electricity consumption. We need to be growing the pace at which we're adding renewables to the grid. And we need to be developing probably half a dozen technologies that don't play a huge role over the next decade, but do play a big role in the following 2 decades. And that includes hydrogen electrolysis, biomass gasification, conversion of the corn ethanol lands to something else more productive over the longer term. What are the other big ones? Carbon capture and sequestration for cement and for power plants and for certain other activities. probably forgetting a few more. But these are technologies that often show up in a big way in our scenarios in the 2040s and 2030s and 2040s, but really are not, going to be cost effective unless we take some effort over the next decade to develop them. So how do you do that with policy? That's the next question, and I don't have I have some ideas, but I don't want to speak for our report because we're trying to sort of stay silent on that question right now. We're actually going to be commissioning policy reaction pieces to this and letting others to put their views up there. And if anybody here is interested in writing one of those, please let me know. We can get you a kind of a look at the report, and you can say, this is what I think it means for policy. So, yeah.
So just in thinking about the clean, firm resources and then sort of putting the whole team together.
Yep.
And where the scale of those decisions would be made. Some of the, I mean, we talked about the energy master plan at the state level. You talk about, I guess, sort of like the reliability, the energy, electricity reliability entities like PJM and the role they would play here. And you talk about challenges of the utility companies. What about that? Because I've been reading some things about how PJM is, and some of the changes that there have made like renewables a little more complicated. So can you talk about that a little bit? Yeah.
So PJM, for those who don't know, is originally was the Pennsylvania, Jersey, Maryland marketplace. It's actually just PJM interconnection now because it extends all the way to parts of Indiana, Illinois, Ohio, et cetera. So it's a big region. It's the largest electricity market by volume and population in the world. I think if it was its own country, it would be bigger than any European country, I think, in terms of electricity sales. So it's a huge electricity market region. And PJM is in charge of both safely and reliably operating the grid and operating all the electricity markets that help that happen. So they have two functions, plus planning long-distance transmission. So big role. They're headquartered down in Valley Forge, PA, so not too far from here. So recently, PJM proposed a new rule, which is designed to, they say, protect the pricing in their what's known as the capacity market. So they pay for short-term energy, and they also pay for long-term capacity, arguably for those sort of firm resources to meet that peak demand that I was talking about. And what they said is that any state-subsidized resources, we're going to reprice their bids because we're worried that those subsidies distort their bids in that market, and it's unfair to do that. That they're depressing, it's states exercising their market power to depress the price. That was the justification. And therefore, we're going to take that price depression out, and we're going to reprice the renewables or the nuclear plants that are subsidized by states like New Jersey, and we're going to price them back up to what we think their sort of natural level is. And what that does is potentially kicks a bunch of them out of the queue and replaces them with natural gas plants, primarily some coal plants, that we were buying that we don't really need. So we're buying them because they think it's fair, but we're not buying them because we need them for reliability. The fact that the subsidy makes them cheaper should just mean that state ratepayers, taxpayers in New Jersey are making it cheaper for capacity for everybody. Why is that a problem? So what it's going to mean is more revenue for natural gas plants, less revenue for state-subsidized clean energy resources that we want to add to our mix. And this has created a huge fight between states like New Jersey and Virginia and Maryland and others that want to make progress towards clean energy, have these big, bold goals, and PJM, which is trying to kind of protect its existing environment. And this has gone to FERC, and then FERC, which is the Federal Energy Regulatory Commission, has traditionally been very non-partisan, but in this administration has become more and more trying to put their thumb on the scales for fossil generation. So it's kind of a big mess right now, and we don't know how it's going to resolve. Illinois has active legislation to leave the PJM capacity market and take responsibility for its own reliability. New Jersey is considering the same. So, this could blow up the whole thing. But what it's revealed is that we have these non-governmental, stakeholder-driven organizations that sit at a really critical juncture in our electricity system. And they face a really key choice because some states are pushing very clearly in one direction. And for multi-state ISOs like PJM, you have states like Ohio and West Virginia that are very much not. So what do they do in that environment? Do they facilitate the transition? Do they protect the status quo? They do something in between. And they have a huge influence over the outcome. And so I think this is going to be a bigger area for discussion and debate going forward. And ultimately, it'd be nice if those system operators were actually incorporating into their marketplace the kinds of clean energy goals and not pushing them away. That's my view. Yeah.
So that was one version of the story. Mm-hmm. Another version is economic efficiency, the monopsony argument. States can adjust. They can put a price on greenhouse gases. Mm-hmm. All that would flow through. The problem is really not PJM or the FERC. It's lack of federal policy.
Well, that would help too.
If there was
Yep.
federal policy, it would ripple down.
Yep.
The environmental is stuff done by the EPA, not by FERC.
Yep.
There's certainly partisan at the FERC. I'm not defending the current administration
Yep.
for that. But, you know, there's a long list of economists who've gone through this argument in terms of the monopsonies. So you have
Yeah, I used to work for one of them.
You have two market failures at once. You have the not pricing the greenhouse gases, and you have this monopsony.
Yep.
So
Yeah, no, I'm very familiar with that argument too. So I spent the last year with Bill Hogan at the Harvard Kennedy School before coming here, and he's one of the ones who's written amicus briefs on the side of a bunch of others. Yeah, yep. So we've had this debate. My view on this is that, and this is the court's view as well, by the way, which is that states have a legitimate public policy purpose to deal with attributes that are not priced in the electricity market.
Right, so
Right?
New Jersey went through this on natural gas power plants.
Which was
They wanted
not,
to fund-
right, which they lost because they were trying to do the thing that the market is supposed to do.
That's right. So,
And states have simultaneously been upheld multiple times for subsidizing clean energy attributes
no, that's right.
for their environmental
Draw
attributes.
this line between retail and wholesale, as we see.
But the federal courts have been clear about that. So my view is this is an issue for the courts to decide, not for PJM, which is a non-governmental, stakeholder-driven organization, right?
PJM is a utility regulated under the Federal Power Act.
Well, they're a RTO regulated by the FERC,
They are a
yes.
utility
But
regulated
yeah,
under the Federal Power Act.
yeah.
Okay, I want to give this
Yeah,
one last
okay.
question because he had his hand up first,
Yep.
and then we're going to have to kind of wrap it up here.
I have a question that's compared with the electric cars. The internal combustion car or the cars run on oil were the only cheaper but convenient because the oil has much more higher
Much higher, yeah, energy density.
than
And faster refueling time, which is
it's easy.
probably the bigger factor, yeah.
So it is possible for the policy to change people's preference on cars.
So yeah, so I think it's actually the refueling time that's a bigger issue. The energy density is getting close to parity, partly because the internal combustion engine is less efficient than the the electric vehicle
Nowadays,
system.
the gasoline is 10 times.
Yes, but if and I agree. So obviously it's more energy dense. But if only 15% of that energy gets to the wheels instead of 50, it doesn't matter how much you're carrying in your tank. I mean, it does matter, but it's diluted. So the energy density, I mean, we're seeing electric vehicles getting to close to 300, 350, even close to 400 mile range soon. So the range issue, the fact that I can carry on enough energy to go far isn't as much of an issue. It's that it takes me many hours to recharge instead of 5 minutes. And even at fast charging, it takes me 15 or 30 minutes and I have to wait for the fast charger. So I think that's the biggest impediment. I've always been of the view, I mean, I'm not a market researcher, so I don't know if this is true or not, but the plug-in hybrid vehicles of a mid-sized SUV that's a plug-in hybrid with a 60-mile range, and then it switches to gasoline would probably be a pretty killer market segment for the US market. But many other people are perfectly happy with EVs, and what we seem to see is when people start driving them, they're not just, they're inferior in this one particular way, but they're actually superior in many other ways, right? They're way faster off the get-go, they're quiet, you don't have to go to the gas station, which is a plus for most people. So, and they're cheaper to maintain over time, cheaper to fuel. So anyway, there are pluses and minuses on both sides, and I think as people get more experience with them, people tend to love their EVs and never want to go back. So I think, if we can continue to sustain the uptake of EVs through subsidies and through CAFE standards for the next decade, my guess is by the end of that decade, it's going to be a pretty even fight between the two. But we'll find out. I think that's.
So this question is related to the direction of the technology development. So what's the direction of the civilization development? So the civilization, as in my opinion, the development of civilization or technology is meet people's needs with less and less effort.
Yeah.
Makes us easy to satisfy our needs. This is the direction of the civilization and the technology. But the common car is just easier.
Well, I mean, that's your view, right? I think as I mentioned, there are some things that's easier, primarily refueling. There are a lot of things that it's not easier, including refueling, right? You have to go to the gas station all the time. Yeah, you don't have to change the brakes, you don't have to maintain the oil, you don't have to change the transmission after 100,000 miles. So, life cycle ownership, there's a lot of conveniences to electric vehicles. So it's not a solely inferior product. It's inferior on one specific measure and superior on many others. And so I don't know that it fits nicely into a teleological societal direction, right? It might, but.
All right,
Yeah.
I'd like to give Jesse a
Great. Thank you so much.